Okay, welcome everyone. Welcome everyone to the ICTS Colloquium. This is a monthly colloquium series that we have, and nowadays we've started embedding these into the program as a way for ICTS members to also know about what's going on in the program. As you can see today, we will have a discussion on integrable combinatorics. I want to hand it over to Renat, who will introduce our speaker for today.
Okay, so thank you for organizing the colloquium. So Philippe Di Francesco probably needs no introduction, but I'll introduce you anyway. So Philippe is a dual member of, IPH, Institut for Theoretical Physics in Saclay, and math department at the University of Illinois in Urbana. And Philippe is a graduate of École Polytechnique and has degrees from in math and physics from Orsay, has a PhD in habilitation from Paris-Saclay, I think, and has been formerly a plenary ICMP speaker in 2012 and an invited ICM speaker in 2018. So currently, he's also, I should give a shout out to his recently late sponsor. So he's Morris and Gertrude Fine Distinguished Professor. Mr. Fine just passed away, so that's why I think we should mention him. So Philippe will speak about it, integrable combinatorics, and if you don't know what integrable combinatorics is, that's because it's Philippe's terminology, so he will explain.
Okay, thank you. Can you all hear me fine? Okay, so I thank the organizers of the Colloquium for this invitation and those of the program for inviting me to come here. So today I want to discuss how the property of being integrable can kind of change the face of a subject, right? So here the subject is combinatorics, but it could be something else. But we've done physics already, so let's do combinatorics for a change. And so I'll try to show you a bunch of examples which mainly come from physics, but which really address pure combinatorial problems, and in which some property of the problem, essentially related to its symmetries, will make it integrable and then amenable to all sorts of techniques which were perhaps not so standard in combinatorics. Okay, so I want you to see the interplay between these two things. Okay, so this is the plan, more or less. So I want to just introduce you to the words, right, structures and tools. And then I'll do these 4 examples. So the first one is Lorentzian gravity. So 1 + 1 dimensional random surfaces. Then planar map geodesics. So that's more like 2-dimensional random surfaces. Then combinatorial problems arising in cluster algebras in relation with integrability. And finally, some more kind of standard integrable systems, starting with a 6 vertex and then going on from there. Okay, so what kind of combinatorics am I looking at? I'm looking at basically enumerative combinatorics is just counting, right? You have some set of objects with some definitions, and you want to know how many there are. So usually it's a finite set, so you can count. Okay, there's a branch of combinatorics which is called algebraic combinatorics, and actually which itself branches into many different things. But I would summarize it as it's a place in combinatorics where you use underlying algebraic structures. So I wanted to give you a very simple example. So here is my example. So the objects I want to count are what's called dict paths. So it's just, if you want, it's random walks that can go up and down, right, on some half line, right? So I can go up here and down, but I can never go below 0, right? And now I just show you what I did. So I went up, down, down, etc., right? And so we want to count the set of paths that go from the origin and end up at the origin after a certain number of steps, which you can figure out very easily has to be even. So 2n steps. And now I want to introduce a little more interesting thing in there. Instead of just counting paths, which would be just purely enumerative, I want to put a weight, right? So this idea of putting weights comes from physics. You put Boltzmann weights, and then suddenly things start having a physical meaning, okay? So here my weight will be a weight Q per box in the box decomposition of my path. So you see, I just decompose the path into unit squares that fit under the path, and I want to weight these paths with this weight, okay? So here is how to use algebra to solve such a problem. There are solutions that don't use algebra, but I find this one more elegant. So you introduce an algebra, which is called the Weil algebra, with two generators up and down, right, U and D, and U and D are subject to this commutation relation. Up times D is Q times D times up, right? And so this is the picture, right? So down up would be just a corner like this, and then up down compared to down up is just adding a box, right? And I want to count boxes with a weight Q, so this is perfect to do that, okay? All right, so when you have an algebra, first thing you want to do to be able to work with it is a representation. So here you're going to basically introduce a vector space indexed by non-negative integers on which U and D will act as operators, linear maps, and this is the way you want them to act in order for this relation to be satisfied. So when you go up, you just add up 1 to the index of your vector, but when you go down, you multiply it by some power of Q. And of course, when you act on 0, you want 0, because you want to never be able to go below 0, right? So the -1 vector doesn't exist, or is 0. Okay, and so now the formula for Zn is particularly simple. It's just all the ways of going down and up, right? So it's down plus up 2n times, so to the power 2n, and you just have to sandwich them between 0 and 0, because you want to start at 0 and end up at the vector 0, and that's it. Okay, so here is an example of how to use algebra to solve a combinatorial problem. Okay, just a small example like this. Okay, so now what about integrability? Well, integrability is in relation with symmetries. Okay, so loosely speaking, a system is going to be integrable if it's sufficiently symmetric, right? So it has to have a sufficient number of symmetries that will give rise to conservation laws that simplify the problem. And if you have enough of those conservation laws, then the problem is going to be called integrable. Now, there's many ways of being integrable. You can be classically integrable, UV integrable, quantum integrable, and I'll show you examples of all this, but I prefer not to bore you with definitions. Right? So another way of being integrable is the fact that the problem inherently is based on what's called a flat connection. So I'll give you an example and you will see what I mean by that. And another way of thinking of those symmetries, if you think in physics in terms of Hamiltonian systems, for instance, so a system driven by a Hamiltonian, is basically operators that are going to commute with this Hamiltonian. So if you have sufficiently many commuting operators that you can simultaneously diagonalize, then this will guarantee integrability as well. Okay, so this is okay. So what kind of objects are we going to look at? Lorentzian triangulations, planar maps, friezes, and vertex models. So this morning there was an introduction to vertex model, very useful. So now you all know, I mean, those who were here this morning know that vertex models can be also represented in terms of paths. What kind of tools? Well, the tools from combinatorics are generating functions, bijections, classical tools of combinatorics. Coming from statistical physics, there's the notion of these commuting transfer matrices, okay? And networks, we saw that also this morning, and Yang-Baxter expression, which we also saw this morning. Okay, so let me start with the first problem, which is the enumeration of 1 + 1 dimensional Lorentzian triangulations. So you basically want to consider a discrete version of a space-time in which space is random, but time is a lattice, right? So it has to be well ordered in time, so you have time slices, okay? But within each slice, you have a random space. So to describe this random space within each slice, I just put a random triangulation of a strip, right, between these two timelines here. And the randomness is just in how the triangles that you're going to use. So a triangle has to be attached to the top and the bottom, so there's not that many choices. One edge must be on the top or one edge on the bottom, and then the opposite vertex is on the opposite line, okay? So you have a succession of arbitrary up-pointing and down-pointing triangles, okay? Question is, can I say something about this? Okay, so first thing you can think of is use the dual picture, okay? So the dual puts a vertex in the middle of each face and a dual edge, right, connecting two neighboring faces. It's pretty easy here. You can actually associate each bar, vertical bar, to a lozenge. So here maybe it's easier to see, right? You have two triangles which share an edge here, up and down, right? Pointing up here, pointing up here. And this edge. Is there a question? Okay. So, okay. So that's the dual graph, okay? Now my claim is that the dual graph is a tree in hiding, okay? So let's see that. And the trick here is to squeeze. Okay, so what I'm going to do is I'm going to push the edges to the left, okay? But the rule will be that whenever you have an edge on top of you, you cannot go beyond it, right? It's stopping you. So these three guys, for instance, can be slided to the left, but they are going to be stopped at this point, okay? So let's do that. We find a tree. Right, so the edges that you were sliding to the left are actually those that are attached to the same vertex in the bottom. So let's look at these three up here. They correspond to these three edges, 1, 2, 3, which I pushed to the left, but they were stopped by this edge here, and so they end up being these leaves on the tree, okay?
So you deleted the horizontal edges also?
Yes, I can forget them completely, but they're still here, right? They're the level inside the tree, right? You have a hierarchy in the tree. So to each vertex, you can associate a number, which is just the height here, or its distance from the roof, if you want, and that will be its time slice, okay? So it's still there, it's just hiding, yeah. Okay? So random triangulations, Lorentzian triangulations, are trees, in fact, okay? So now what I'm going to show you is that those trees are integrable somehow. Okay, so why? So let's try to compute this thing by using a classical object of statistical mechanics, which is called a transfer matrix. So the transfer matrix describes how locally to go from one time slice to the next. Okay, and so here is the picture in the dual, right? In the dual picture, you had a bunch of up-pointing triangles from this slide, right? So the up-pointing triangle, let's say, which are on the bottom here, and then a number of down-pointing triangles interspersed between them, right? This is how you do those time slices. And so this dually, this is described in this way. So let me think now of an up-pointing triangle coming from the bottom as states, okay? And so pretty much like I was describing my representation of before of my Weil algebra with vectors indexed by integers, here we have integers that are going to index states. Okay, so the state is I up-pointing triangles connected to the bottom line. Okay, transferring to j down-pointing triangles connecting to the top line, right? And now the question is, how many of these can I generate, right? And the answer is super simple. It's just binomial, right? It's how many ways of arranging these guys in between those, right? So it's shuffled, okay? So now I can figure and when I want to go across a timeline like this, I know exactly what to do because these edges, which are represented here as cut in two, right? These are half edges. If I prolong them, they're going to hit the next line and they will be, of course, connected to a triangle pointing the opposite way, right? So each edge is actually a half edge. And so I can now concatenate the various guys, right? And pairs of half edges are going to create edges for me. And I will describe the entire thing by just actually multiplying this matrix with itself a certain number of times. So that's the role of this transfer matrix, is to have a sort of local transformation which once iterated, will create the entire configuration, okay? So my transfer matrix is really simple. It's the infinite matrix of binomial coefficients. So I and j are non-negative integers, okay? So you have to imagine this infinite matrix, okay? Now we can make the model even more interesting by not just counting those guys, but actually introducing the notion of curvature, okay? So the curvature has to do with how many triangles can I cram around the vertex, okay? So another version of that is how many triangles are going to point in the same direction in succession, okay? So I'm going to put a different weight, A, to successions of pairs of triangles which are connected to one another, right? And which point in the same direction, okay? They're adding up curvature at the vertex that they share on the top, okay? And same thing for the bottom pointing triangles, okay? I will also put an area weight, that is a weight per triangle. So in the dual is just a weight per t or upside down t. And now I can compute the new version of a binomial coefficient, right? So my previous counting was just a binomial coefficient. Now it's a refined binomial coefficient, which is this, okay? So it's not difficult at all to put all the weights. So the fact that g comes to the power I plus j, for instance, is completely obvious because you have I plus j points on this line, right? So the area in terms of number of triangles that you have connecting to this line is I plus j. So there's a g to the I plus j. Now the dependence on A, you have to do a little bit of work, but it's not very difficult. Okay, back to combinatorics. One likes to summarize numbers, one likes to write their generating function. So this is maybe not so standard, but when you have a matrix, you can do the generating function of its matrix elements, okay? So this is infinite, right? So I do this generating series, and I find out that because of these binomials, everything is calculable, and it's actually a very nice rational fraction, okay? So I call it Ft, right? T is the matrix, Ft is the generating series of its matrix elements. Okay, so just a little bit of calculus using this representation. How do you represent the product of two matrices? Well, I claim it's just the convolution of their generating series, right? And this is the formula, right? So if you write exactly what this means, this is exactly the infinite sum that you need to make to do the product of the two matrices, okay? So it's easy in this way. Once you have a generating series of the matrix elements, it's very easy to compute products of such matrices, right? And this transfer matrix is something we want to take products of. But now comes the interesting thing. If you compute the commutator, so you just do a product in one direction minus product in the other direction of two such transfer matrices at, say, G and A for the first and G prime and A prime for the second, okay? Well, you find that this commutator vanishes if and only if a certain function of GA is equal to the same function of G prime A prime, and this is the function. So this is an elementary calculation that you do by using convolution on this particular rational function, okay? So it's really basic. Okay, so what this means is that provided G and A are related in the way that this thing is a constant, right? Phi independent of G and A, right? So along this curve, you can think of it as a curve in AG space, right? All the matrices are going to commute. So I provide you with an infinite set of commuting transfer matrices, okay? That is going to make the system integrable. So trees, to summarize, I've taken trees, I've put some weights on those trees that were inspired by their interpretation in terms of a Lorentzian triangulation, and now, putting parameters connected to those weights, I produced for you a set of commuting transfer matrices. So once you have commuting transfer matrices, it's really easy peasy to solve. So you decide to call a name this constant function phi, and it's called Q plus Q inverse for good reasons. Then you change variables from A and G to lambda and Q, basically, in this way. And then you can rewrite entirely this generating series of the matrix elements in this way, which makes it completely explicit what the spectral decomposition of my matrices, infinite matrices are. These are the eigenvalues. These are the eigenvectors, left and right, right? And as you can see, the eigenvectors only depend on these Q and M, and the eigenvalue depends on lambda, right? So we have kind of split up in between eigenvectors and eigenvalues, and the eigenvalues depend on one more parameter, and that's the parameter which describes this infinite set of commuting transfer matrices, because they all share the same eigenvectors but have different eigenvalues. And once you've done that, you can actually compute something, right? So you can compute a partition function of Lorentzian triangulations with I lower triangle and j upper triangle and n in between time slices very easily, because you have the eigenvectors and you have the eigenvalues of this transfer matrix. So you can just compute everything you like, okay? So to summarize, I've shown you an example of a combinatorial problem, which you could interpret in various different ways. How physics helped me decorate this problem with parameters, and how the existence of these parameters allowed me to come up with some infinite set of commuting transfer matrices which make the system integrable. Okay.
Question.
Yes.
So if I'm doing Euclidean.
Yes. It's next. It's coming next. Thank you for your question. All right. So Euclidean quantum gravity. Yes.
What is the interpretation of this fact that there is this curve that is integrable? Is there a meaning in terms of the original physical problem that this?
Well, you see, every single one of these matrices will commute with a basic matrix you define your model with, right? So you can think of them as symmetries of a model. So you have an hidden infinite symmetry of your original problem, right? That's...
and maybe I'll phrase it another way. I mean, it gives some relation between the cosmological constant and the curvature and the area terms. So, so is that relation somehow significant in the continuum limit? Maybe you will talk about it. But is there a special?
Well, yeah, people have been studying Lorentzian gravity with these types of models, right? So, yeah, definitely it has some physical content, but I have no time to describe that. Okay, so the question of Spenta was about another type of gravity, which instead of being Lorentzian is Euclidean, but is in which really space-time now is really two-dimensional, right? So it's going to be random in all directions, if you want, okay? So this is the usual picture that one gives. So this would be the regular lattice, and then this is the random lattice. So it's even more random than that, but it can even have some topology, right? Some interesting topology. So from a two-dimensional lattice model, you want to go to a two-dimensional random tessellation, on top of which you're going to put your favorite model. So here I just put a sigma just to point to maybe Ising model or something like this, which is a statistical model that lives on the vertices or edges or whatever, some statistical model on your lattice, original lattice, and now you want to randomize everything. That is, the lattice becomes random, and on top of this random lattice, so you're going to sum over all the possible lattices, and for each of those lattices, you're going to sum over all possible configurations of whatever system you want to put on there, right? And there's a very interesting set of solutions, right, which used all sorts of, so from the 90s, which used all sorts of technology like matrix models and came up with exact solutions, series expansions, integrability manifested itself in various manners, in particular in the fact that these guys were tau functions of certain hierarchies, etc. Now, the question I want to address now is a bit different, has to do with what's called intrinsic geometry. So I want to figure out what happens if I look at points at a fixed geodesic distance from one another, and now I sum over all the random surfaces that realize this same geodesic, okay? So I want to fix the geodesic distance and study what's going on. So here is the model for discrete random surfaces, at least in genus 0, right, so on a sphere. So here I'm looking at the dual of what's called a quadrangulation. So it's a planar map with 4 valent vertices, as you can see. So made of faces and edges, and the plane of the picture is actually the plane on which things are represented. And so tetravalent, and moreover, I impose 2 sort of boundaries, right? The fact that there are 2 dangling legs here, right? So univalent vertices, if you want. And these are going to be the vertices I measure things at, okay? So I'm going to count those objects, again, with a weight, which is g per vertex, which dually would be g per square in my quadrangulation, which is, again, an area factor, right? Area of a dual map. But more interestingly, what I want to keep track of is the geodesic distance between these 2 marked legs. Okay, so what's the geodesic distance on a random map? It's just the smallest number of edges you have to cross in a path that goes from one to the other, and that, of course, avoids all the vertices. Okay, so here I gave you an example of such a path, right? And so the geodesic distance between these 2 points is 2, given by these 2 intersections with a dashed line. Okay? So now, combinatorial problem is try to figure the generating function for maps, right? Such that the 2 legs are at a distance, geodesic distance, less or equal to n. Okay? So that's the question. And here is the answer. The answer is both combinatorial and physical, so it's quite interesting. So first part is combinatorial. There's a bijection between those maps and trees, but not the trees that we've been seeing before, decorated trees, which I think are called by Schaeffer blossom trees, because they have 2 types of leaves, right? Black and white, okay? So here is the algorithm that goes from the left to the right. You go around the external face of your map, right, with a pair of scissors, and whenever you see an edge, you cut it. And when you cut it, you replace the part of the edge you come from by a black leaf, and the part of the edge you go to by a white leaf, okay, black-white. So at the first stage, you go around like this, and you will cut 1, 2, 3, 4 times, right? 2, 3, 4 times. And then you continue, you go on. So at the second stage now, I can go inside, right? And now I can cut this guy, because there's a loop here, and I can cut it. So I cut it, and I cut the next, which is here. And then I go around, and I cut the next, which is here, etc. And I go this way like an onion, right? You peel an onion, and you stop when you get a tree. And that's a tree, but it's a blossom tree, okay? So what do? On top of that, you add up a white leaf at the old root, and you promote this second guy as the new root. So the root was the dangling piece that was inside the outside face, okay? So you've created this monster, right? It's a tree, a blossom tree with black and white leaves. And now I can interpret Rn entirely in terms of those trees. Okay, so I do this picture. So you see there's one white leaf which is singled out, right? And all the others, they can be paired together, right? Because they can reform all the edges of this map by being reconnected. But what's interesting is those that, to be reconnected, need to go around the root of the tree. These are the guys that are above the head of the root here, right? And allow to connect you to the outside. So these are precisely the edges to be cut to recover the geodesic distance, okay? So by bounding the geodesic distance by n, I'm bounding this number of closures passing above my head by n, okay? So I have this picture. So now with those pictures, it becomes super easy to count. And here is the counting, right? So you want to count Rn. So either you have a very trivial tree which just has one leaf, right? So it counts for one, or it's more complicated, and then you start looking at the various things you can encounter when you go around the tree, right? So if the first thing you can see is a black leaf, you're in this situation. If not, you're in that situation, etc., right? So you have three possible situations. And each time you have to count, to see how many of those leaves you can saturate black and white together, and you will see very easily that this is what you get. Okay, so you get a recursion relation for this Rn in terms of n, which is the discrete geodesic distance. Okay, now the initial conditions are a bit bizarre, right? So there's a condition at -1, which is telling you that there is no distance -1 object, so it's 0. But there's also the infinity, right? So when n goes to infinity, it means I don't have a bound on my geodesic distance, so I'm just counting the maps. And the counting of the maps is just solving this equation, right? So it's very simple. Okay, so we have these two boundary conditions. Okay. So why am I saying that this problem is integrable? Well, look at this equation, okay, with these boundary conditions. I claim that there exists a function phi of two variables, x and y, right? And this is the function, which is such that the difference of the function at two consecutive values of r, right, is up to some factor, the equation itself. Okay, so if r obeys the equation, this is 0. So phi is a discrete first integral of the equation. Okay? And that conservation law is a sign of integrability. And now is the solution. There's an exact soliton solution to this problem, which is that Rn take this form. So we saw earlier today some talk in which we had solutions to discrete systems. And, maybe we didn't see solitons yet, but maybe we will in the future. So this is what soliton solutions look like. And they are directly related to the integrability of the problem. So there's a soliton solution that you can interpret as the generating function for those maps with legs at bounded geodesic distances. And once you have that, you can take continuum limits, you can do physics. But I'm stopping here because I just want to show you the mechanisms that are behind the combinatorial problems. Okay? So let's switch to another problem now. So this one will be in relation with cluster algebra. So it has the name of A1 T system. So it actually was born in physics also in relation with functional relations satisfied by transfer matrices of spin systems. But you can forget about all that and just concentrate on the equation itself. It's a very simple, so again, it's two-dimensional, right? Because it has two integer indices I and j, right? And so this Tij satisfies this recursion relation. So ij is in these two, but the parity is conserved. So you decide that I plus j is always even, okay? So you can think of this as a recursion relation in some discrete time, so called j the time, right, and I the space, right? So from time j and time j minus 1, you can get time j plus 1, right? So it's a certain difference equation which describes a time evolution. Or you can think of it more as a 1 plus 1 dimensional problem in which I just wrote the axes I and j, and as I plus j is 0 mod 2, I'm only on a square lattice which is tilted by 45 degrees. And I want now to solve this equation, okay? So the thing about this equation is that first you have to figure out what the initial data are that I should feed it with so that I get a unique solution, right? And so it's not very difficult to see that the initial data assignments are just you assign the value of Tij along a curve, okay? And this curve is just a broken line in this lattice I just described, right? Which satisfy ki plus 1 minus ki in absolute value is 1. Or basically it's a path, right, that can go up or down, okay? So you choose your favorite path, which is infinite in this case. You decide on values you assign to the vertices of that path, right? And that will be the initial data that you feed your equation with, okay? And then you turn the crank. That is, I claim that Tij of A is defined everywhere now, okay? You just have to iterate sufficiently many times this equation, okay? So there's a cluster algebra formulation of this, which amounts to first transforming my initial data step surface or broken line into a quiver, okay? So all the arrows point up. So that's a quiver. And at each vertex, I have a variable, okay? So this is the setting of cluster algebra. It's a set of vertices of a quiver at which you have variables, and then you are going to evolve them, okay? So applying the equation that I had before is actually going to be the evolution, the mutation of this cluster algebra, okay? So basically that's what's happening, right? I had 3 values here, and I'm going to get the 4th one out of my equation, okay? And once I get the 4th one, I forget about the previous and I replace it by the new, but now the quiver has changed, okay? And that's my cluster algebra, basically. So you don't have to know much about cluster algebra because I'm going to define everything here. So the B prime, so B was the old value, right? And now the new value B prime is such that the product is AC plus 1. So the two guys at the level plus 1. Or another way of thinking about it is to say that the plaquette here, if you consider the vertices of the plaquette, their determinant is equal to 1, okay? All right, so now you can see that applying locally my evolution equation allows a sort of reptation of a broken line, right? I augment it by 1 box here, 1 box there, and I can go anywhere like this, okay? And what I learned from the fact that this is an actual mutation of a cluster algebra is that the Tij of A that I'm going to end up with very far away, you know, with I and j very large away from this line, will always be a Laurent polynomial of the initial data, okay? This is the key property of cluster algebra. Okay, so now I claim that this system is integrable independently of whether it's expressible in terms of cluster algebra or not. So to make life simpler, I've decided to take 1 as value everywhere on my initial data broken line, okay? So let's try to compute the values of Tijk in the plane, right? So clearly this guy here is such that this times 1 is equal to 1 times 1 plus 1, so it has to be 2, okay? All right, so yes.
Evolution happens at all places simultaneously, that it can?
You choose. You can evolve anywhere. My problem is to find the value of Tijk here, up here. Okay. So to reach this point, I have to do a number of boxes. So sufficiently many that I can reach this point.
Okay.
But there's no, I mean, the order, of course, you cannot do the mutation here before you do all the mutations below, right? So there's a certain order, but it's not deterministic in a sense. Okay. So, okay, and so you go, so let's see this 7, for instance. 7 times 1 is 3 times 2 plus 1, okay, and so on. 37 times 3 is 10 times 11 plus 1. Okay, you check that. All right, so, but what's remarkable already is that in this thing, right, if I defined my new variable here as 10 times 11 plus 1 divided by 3, it seems that it's a miracle that it will be divisible by 3, right? And that you get an integer here, right? But that's really the property of a cluster algebra. The fact that every value is a Laurent polynomial of the initial data, what's a Laurent polynomial of 1? It's an integer. Right? So that's why everybody in there is an integer. But it's not guaranteed completely, right? Because at the next stage, this guy here will be obtained by multiplying 64 by 100, adding 1, and dividing by 37, right? So you have a divisibility property, which is highly non-trivial, and which comes from this cluster algebraic formulation. Okay, now integrability. So I ask the audience to concentrate on the 3 lines I've singled out here, right? And can you see a pattern? Yes?
So we won't have, because you're taking infinite Prisma mapping, like there are no 0 rows or columns at the end.
No, it's infinite.
That's why
Complete.
there won't be any periodicity.
No, there is no periodicity here, okay? But there is something.
Yeah.
So what is there? I claim there's a conservation law here. Can anybody see it? Okay, let's concentrate on these 3 numbers. 3 in the middle, 10 and 2 on the edges. Now here, 11 in the middle, 37 and 7 on the edges. Anything popping out?
Some of the edges.
Absolutely. 37 plus 7 is 4 times 11, right? But 10 plus 2 is 4 times 3. 3 plus 1 is 4 times 1, right? So 4 is a conserved quantity along this triple of lines. Bravo! So you have this linear recursion relation between the numbers here, right? But it's much better than that. It's every triple in the 2 directions, right? But you see the number can change. Here it was 4, now it's 3. And actually the number is determined by the shape of the boundary that lies below your triple of lines, right? So here, for instance, is 2 because your boundary is flat, right? But here there's an indentation in the boundary, so it's 3. And the one that was 4, I think it was this one, it has a bigger indentation, right? So the shape of the boundary determines the conservation law. So you have 2 infinities of conservation laws here, right? So it's very, very integrable. So, okay, so now I'm going to show you the solution of a problem involving another construct, which is a construction of a flat connection. Okay, so I want a matrix representation, 2 by 2 matrix representation of what happens on this broken line of boundary segments, okay? So edges of this broken line will always join 2 vertices with values, assignment values of initial data, A and B or C and D, whatever. So I define a down matrix and an up matrix in this way. So the down is upper triangular and the up is lower triangular, I'm sorry. That's how it happens. And so to a succession of such edges, I will associate the product of the matrices from left to right. Okay? And now here is the beautiful thing that's happening. D times U is equal to U times D if and only if the equation of evolution on the plaquette is satisfied. In other words, this matrix formulation represents completely my recursion relation for this A1T system. And of course, I chose my previous example on purpose to show you that it's kind of the same story that's going on. But instead of having a Q commutation between two Weil algebra elements, it's a bit more tricky, right? It's 2 by 2 matrices now. Okay. And you can interpret this as down, up is up, down. It's really upper, lower is lower, upper, which is what's called a refactorization problem, right? You have a matrix, you do the LDU decomposition, and then you take L, you put it on the other side, the U, you put it on the other side, and you LDU decompose it again, right? And this is what you're doing. Okay, so now that I have this matrix representation, I claim that the solution is very easy. The solution Ij, I project Ij, the point by some light cone projection onto my initial data. So first of all, you see that the infinite parts of the initial data on the right and left don't count, only those inside this cone count. And then Tij, I claim, is just the product of the down or up. So here it's a down followed by an up, down, 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 etc. With assigned values at the vertices, right? And then I take the matrix element 1, 1 of that, and I have to multiply by the last initial data, which is here on the bottom. Okay? And that gives me Tij. Why? Well, the proof is one line or one picture. It's because to reach Ij, I need to go up as much as I can, and then I go down as much as I can, right? So once I reach Ij, I will have a decomposition in terms of up, 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 and then down, 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 okay? But because of the local relation that I have here, this matrix representation is a flat connection. It means it's independent of the path you're taking to go from this point to that point. So the first path is, of course, going from the bottom, okay, and that's what I have written here, but any other path will do. And this top path is particularly nice because all these are up matrices, which are lower triangular, and all these are down matrices, which are upper triangular. And so doing the product of upper followed by lower followed by a product of upper just selects only one matrix element each time, right? So you have a collapsing product of terms which ends up with just the value at this point. So it's a very, very neat thing. So having computing this by the red path, I know that the answer to this computation is what I'm after. It's the value of t at Ij. And now I can express it in terms of the other path, the blue path, which is in terms of my initial data. Okay? So the flatness of this connection allows you to solve entirely the problem in a pretty explicit manner. Okay. So to make the contact with Misha's talk this morning, you can reinterpret these matrices as actually being network matrices. So for those who don't know about this, you just have a graph, right, with entry vertices and exit vertices labeled, in this case, 1 and 2, and then a path that goes from the left to the right, so will correspond to a matrix element in this matrix. And so each step of that path will have a weight determined by the matrix elements, okay? And now, if you want, if you consider a product of such matrices, what you're going to consider is a larger, it's a concatenation of all these individual pieces. So here is, for instance, what you get when you concatenate down and up, down and up, down and up, is just this, what I call a flat broken line. Okay, and then the solution Tij, you can reformulate because this was the 1-1 matrix element in a product of these and U's. It's also the partition function of paths that go from 1 to 1 on the particular graph with weighted edges that you have been constructed by concatenating your various D and U pieces. Okay. So it's a kind of visual picture of the solution that I wrote before, right? Now there's a bunch of transformation you can do. So either you think of it as a partition function of paths with certain weights, or you realize that these paths are nothing but domino tilings in hiding, right? So there's a bijection between those paths and domino tilings. And so you have a domino tiling of a strip with certain weights which are related to the initial data values, which I rewrite here, right? And actually the weight is just the product of the AI to the power ni minus 3, where ni is just the degree of the vertex I, okay? So you have a very, very nice explicit formulation of the solution of the problem in terms of statistical sums of over configurations. And this is just the visible part of the iceberg, because in cluster algebra, there's many, many problems that you can formulate in a similar manner with also flatness conditions on certain connections, and which you can solve in terms of dimer models or domino tiling models. So, and, okay, so dimer, yeah, the dimers are just kind of a dual of the domino tiling. So this is the domino tiling and this is the dimer model on the dual graph, right? And so again, you have a local weight, local Boltzmann weight associated to the configuration of each face according to how many dimers are occupying the boundary edges, okay? All right, so, and more generally, you're going to have a succession of these and u's, right? This was all for du, right? It was the flat initial data. And now, more generally, this is what you get. Because whenever you have two D that follow each other, you have to complete the graph in order for it to be bipartite. Yeah, I didn't mention that, but we needed a bipartite graph here, right? So. And to make it bipartite, you have to introduce these extra vertices, which make certain faces hexagonal, right? So the rule is that whenever you change direction, you have a square, but when you go along the same direction, you get an hexagon, right? So 5 has an hexagon, 6 has an hexagon, 7 change direction has a square, etc. And now the solution is just the partition function for dimers on this new graph made of hexagons and squares according to the shape of the initial data broken line. Okay, so very explicit solution. Okay, so that's all I wanted to say on this cluster algebra kind of example. It gives you a glimpse of cluster algebra, but you have to realize this is just the tip of an iceberg, right? It's much bigger than that. Okay. All right, so the last topic I wanted to talk about is more classical for statistical physics, which has to do with integrable lattice models. And so it starts in combinatorics with the introduction of these alternating sign matrices, which were later realized to be in bijection with configurations of a 6-vertex model, which we saw this morning, on a square grid with very peculiar boundary conditions that you have to have arrows entering horizontally and exiting vertically. This morning, there were no arrows, there were zeros and ones, right? So 0 is one orientation and 1 is the other. Okay, so it's in bijection. All right, but then, more interestingly, the same. So there's an enumeration here that you can do, right? Count configurations, number of alternating sign matrices. Well, I didn't describe them, so here I describe the problem. So the problem is that 6 vertex, because at each vertex, you have conservation of arrows entering and outgoing, right? So 2 arrows entering, 2 arrows outgoing at each vertex. Here, it translates into a funny thing. It's almost like a permutation matrix, right? With a 1 per row and per column. But now you have also -1s. But the -1s are such that there's always a 1 above, a 1 below, a 1 on the left, and a 1 on the right. They're kind of protected from the boundaries, right? And so these are these alternating sign matrices. Now another set of objects are called the totally symmetric self-complementary plane partitions. And you can think of them as rhombus tilings, right, of some big hexagon, regular hexagon, with as many symmetries as you can. And so this is the fundamental domain under the symmetries. It's 112. Okay. There's yet another set of objects which are called the descending plane partitions, which can be reformulated in terms of rhombus tilings, again, of an hexagon. Now the hexagon is no longer regular. It has n, n plus 2, n, n plus 2, n, n plus 2. For a reason, it's because there's a hole of size 2 in the middle, okay? And on top of that, you demand that these configurations be invariant under rotation by 2 pi over 3 around the hole, okay? Well, it turns out that these guys, and these guys, provided I take the same size, so n here, n here, n here, right, are counted by the same number, which is this famous formula of alternating sign matrix numbers, okay? So there's all sorts of connections between those guys, except the most important one for combinatorialists, which would be a bijection. And there is still to this day, there's no known bijection. There are attempts to sort of weaken the notion of bijection by, for instance, introducing something like a stochastic or stochastic bijection, right? Okay, whatever it means. But there is no known bijection, okay? On the other hand, there's so much symmetry and so much underlying algebraic properties of all those objects that you can say a lot of things, okay?
So when you say there's no bijection, meaning there's, you can, the final answer is the same, but you don't know how to map.
Exactly, yeah. So of course you have a finite number here, finite number there, there's a bijection, right? But no natural bijection, yeah, yeah. So I call these non-bijections actually, right? These coincidences of numbers. Okay, but okay, here comes physics to the rescue. So here is another problem, which is called the loop model on a semi-infinite cylinder, right? So the idea is that you cover you wrap on the semi-infinite cylinder a square lattice, right? And so on each square face, you draw at random with probability p and 1 minus p, one of these two pictures. So what these pictures do is connect the centers of edges to each other in certain ways, okay? And then you ask questions about what's the connectivity of the boundary points, right? So for instance, the point 2 here, well, it seems to vanish up there, but it's actually with probability 1 going to come down to some other point on the boundary, right? So you have some very interesting observables here. And the observables of the loop models actually involve all these numbers, okay? So I'll show you more about that. Now, the cherry on the cake was something we worked on a long time ago with Paul Justin, and then he worked more with Knudsen on this, which is the nilpotent variety. So you take 2n by 2n complex matrices of square 0, right, as a variety. And so a variety, there's a notion of degree, okay, because the equations, you know, are algebraic equations, so you have a certain degree of a variety. And there's also a notion of multi-degree, because you have, if you define correct action, it amounts to looking at equivariant cohomology instead of cohomology. And you have numbers popping out from here, which are related to these totally symmetric self-complementary plane partitions. So there's a bunch of models of problems here that all relate to one another. So I want to extract one thing, which is the loop model. I think this is the more fun, because the loop model is integrable. Okay, and so I want you to think of this loop model now as again generated by transfer matrices. And basically here is how I want to think of it. I want to think of it as a certain partition function here, which will be the sum over all configurations of my loops on this semi-infinite cylinder. And now, by adding one more row, right, I create a new partition function which has to be the same, okay? So there's an eigenvalue 1, if you want, of this transfer matrix T on this partition function, okay? So to understand better what's going on, you have to describe what drawing at random these two pictures amounts to, right? And it really amounts to considering what's called an R matrix of some UQ-SL2 quantum group, a bit like what was discussed by Wheeler this morning. and that depends on a number of parameters. So as you can see here, I have parameters propagating vertically and horizontally, right? And at the intersection of any two of those lines, I'm going to put a Boltzmann weight, which is coded by these objects. Okay, so there's an underlying algebra again to describe these things, but I have no time to discuss that. But nevertheless, these weights, they satisfy the celebrated Yang-Baxter equation. So the R matrix, which encodes the weights that you're going to put at the vertices of your problem, satisfies this relation. And because of that, the transfer matrix, which amounts to adding one more row of boxes to my picture, right, in the dual picture, looks like this. These transfer matrices at two different values of this horizontal parameter here are going to commute, okay? So this is the integrability of the model. So how does it work? You start with what was called this morning unitarity, which is just the fact that the product of two matrices is just the identity. So I can go from a situation where these two lines are parallel to a situation where they cross two times, no cost. And then what I can do is use my Yang-Baxter relation here to move this intersection to the other side of the blue line, and then continue, okay? So you do that until you reach the other end. But if you look carefully, here T prime is on top and T is on the bottom. But once you've done this, T is on top and T prime on the bottom. And now this guy, you go all the way around and it's going to cancel out again with the other guy to give you the identity. And now you get this identity here. So this pictorial representation is really the justification of this Yang-Baxter equation, right? The Yang-Baxter equation allows you to show that transfer matrices with different horizontal parameters commute. So you have a family now of commuting transfer matrices, and we're back to the same kind of situation as we had in the beginning, okay? Now, how are we going to solve the problem by using this property? Well, okay, what it means is that the eigenvectors are kind of simpler, right? Because they must be shared by all these commuting transfer matrices. So we want to figure out what those eigenvectors are, right? So now here is the thing that will explain this relation here, which perhaps was mysterious to some of you, the fact that this transfer matrix acting on psi is equal to psi, right? As follows. So let's take two lines that pop out at the boundary of my cylinder, Zi and Zi plus 1, and add up across. So it just means I'm multiplying by some R matrix, right? So operator acting on my partition function here, viewed as a vector. And by using the Yang-Baxter equation, I can push this blue dot inside, right? And actually, so much so, but I can push it all the way to infinity, and it disappears. And once it has disappeared, I get an equation, which is that the R matrix acting on the function is the permutation of Zi and Zi plus 1 in the function, right? So you can induce an action of a symmetric group on your partition function by the action of this R matrix on the same partition function. So this is an extremely powerful relation called the quantum Knižnik-Zamolodčíkov equation. Can be solved, and thanks to its solutions, you get all sorts of very, very interesting results. So once you solve these QKZ equations, what you find is the entries of the ground state, which was this partition function for the loop model. But it also gives you the information on the nilpotent variety because it satisfies essentially the same relations, okay, and this equivariant cohomology in certain limits. And it also leads to refine sum rule, both for alternating sign matrices, totally symmetric self-complementary partitions, and descending plane partitions. All these objects that don't talk to each other this kind of model allows you to find refined combinatorial sums on their contents, okay, on their statistics. So this is a very long-going project that was really based on this alternating sign matrix saga somehow. Okay, so, oops, I'm a bit out of time. So, summary. So I hope I convinced you that integrability takes various forms, right? Allowing you to actually solve some non-trivial combinatorial problems in various ways. So in the context of cluster algebra, as I mentioned, this is just the small part of a big iceberg called cluster integrable systems, essentially due to some work of Kenyon Goncharov. But it also includes what's called brain tilings in string theory and quiver gauge theories. Another subject I didn't mention at all is that together with a cluster algebra comes for free the quantization. Meaning that instead of having just variables that I put at my initial data, for instance, I can have operators, objects that are non-trivial commutations. And the mechanism of cluster algebra still goes through. The answer of evolution is still a Laurent polynomial of the initial data, etc. Right? So there's a bunch of quantum combinatorics you can do by using quantum cluster algebra, which is very interesting. There's also a notion of quantum determinant. Okay. So going back to the last subject I described, this Yang-Baxter equation and the QKZ equation, it's allowed to give a new take on known families of multivariate polynomials, and this is what the lectures of Wheeler are going to be about, right? So I mentioned Shaw, Littlewood, MacDonald, and there's still some, on top of this hierarchy of multivariate orthogonal polynomials, there's the Kornwinder polynomials, and they're still not part of the picture. So I think this is a very interesting problem to look at. So what else? Well, I showed you all these non-bijections. They're still to be elucidated. And the only thing I was able to do is add more to the list. Okay, so more puzzles. Then there's, with some choices of Boltzmann weights in those statistical models, you can make them stochastic and then interpret them in probability terms as interacting particle models. And that's also probably the field Wheeler from this morning comes from. Okay, and finally, there's another topics related to all this, which are the limit shapes of all configurations. That is more like asymptotic combinatorics. You want to enumerate very large sets of objects, and not just enumerate, but find their typical shape. Okay, and there is a whole business around limit shapes. Okay, so I think that's enough.
Thank you very much. Are there any further questions?
Hi, great talk. Let's go to the first example you gave of two-dimensional Lorentzian gravity.
Yes.
I'm just wondering, actually, if you add one more dimension to space,
yes.
then I can imagine, instead of triangulations,
yes.
you have tetrahedra.
Yeah.
And
actually,
is there a way of doing that?
Yes. We looked at such things. So let's see. There's a very interesting story which has to do with dimensional reduction and with boson-fermion correspondence, in fact. So you can indeed formulate 2 + 1 dimensional models, which will have some sort of similar transfer matrices and everything, in which now the space version will be some hardcore particle model of some kind or other, right? And indeed, we've been able to compute certain partition functions and stuff like this, right? But if you want to do the most general thing, I think the problem is that you need to have a control on the Betti numbers of your higher tetraedrangulations now, right? Because it's and this is substantially more difficult. So people have come up with matrix models to describe, yeah, okay, so you know that. But I don't think combinatorially people have been able to say anything. But it's, yeah, it's an open problem.
Yeah, thanks. So I was wondering, again, the context of matrix models, where you have, in these large n limits, but without taking the double scaling limit, but just the large but finite n, like in the old physics and so now we understand that there is these topological recursion relations.
Yes.
Can they be formulated as some kind, in this sort of broader picture, some kind of integrability relations?
That's a very good question. So integrability usually manifests itself in matrix models in the form of hierarchies of Hirota type bilinear equations.
Double scaling limit, but away from.
Oh, you mean before taking
there, you have a combinatorial problem they are addressing.
So there's a whole business about this, about map enumeration with various.
So that's what I had in mind.
So I'm not sure you can call it integrability, but I know they have exact solutions. So it must be.
That's my question. Yes. Is there an integrability structure underlying them in some way?
Well, you see here in this problem, the conservation law, which was responsible for everything, maybe that wasn't clear enough, was that on those trees, there's always one more white leaf than black leaves. Okay, and that's a conservation law that if you start splitting your tree into sub-trees and things like that, it's conserved, right? And so it's a sign of integrability. Now, what people do in more modern language about these random maps, of course, they try to study them probabilistically in some limit of large, and then we go to the continuum limit, and you don't want that.
Yes.
But before they reach that, there are some very interesting conservation laws that you also can devise on these combinatorial objects. So I think there's a sign of integrability here too. Yeah.
Any other questions from the audience? Okay, if not, let's thank the speaker again.